GIA correction, which is over here on the right, then the scatter reduces quite a bit, and the standard deviation in these trends is reduced by about half, which is a good sign. But also the mean trend is reduced as well to 1.5 millimeters per year. So now I'm going to add the rates of change as these horizontal bars from the reconstructions that we just saw. So we have the Hay, the Church and White, and also the Ray and Douglas reconstruction, which is on the higher side as well. And those are the rates compared to the rates in the long records. And what I wanted to ask is, are the various estimates of the long-term global trend statistically consistent with the trends from the longest and highest quality records? Seems simple enough.
What's your x-axis 0 to 20?
Sorry, so there's 22 gauges, so this is just per gauge. Yeah, I should have labeled that down there, you're right. So this is just per gauge, and then the trends in millimeters per year. So then I want to know if the various estimates of the long-term global trend are statistically consistent. I just said that. So then the simplest thing to do would be to calculate the standard error in these trend values. So that turns out to be about 0.05 millimeters per year. If you calculate a 95% confidence interval for that mean trend, that's the interval you would get. And you would have to conclude that both the Ray and Douglas and Hay reconstructions are outside that range and are not consistent with the mean of these trends. But this is entirely too simplistic because, first of all, I doubt the standard deviation of these trends is actually indicative of the error in these individual trend calculations. And also, this assumes that the error in these trends are independent. And this is certainly not true because we saw all that large-scale structure in the altimetry data. And I'll show you another process in a moment that leads to large-scale structure in sea level trends or spatial differences in the sea level trends. And this large-scale structure could lead to sampling bias by this only handful of records that are clustered around the global ocean. Okay, so then how can we get more realistic error estimates for these trends from these gauges, as well as the sampling bias? Well, the first thing we need to do is try to get some estimate of the spatial structure in long-term sea level change. And two processes I'll focus on here are changes in gravity due to ice melt, also known as melt fingerprints, and regional and local changes in the density of the ocean, which refer to as steric sea level change. And then the next step would be to assess the probability that the mean trend from the small number of gauges systematically under or overestimates the global rate of rise based on the locations of those gauges and the spatial structure in the sea level trends. So if you're not familiar, I pulled this schematic off the web, and it explains the basic concept behind melt fingerprints. And the main idea here is that glaciers and ice sheets are so massive that they have enough of their own gravitational pull to actually change the shape of the sea surface. So they pull the ocean surface towards them. So you have a big ice sheet in some area, and the sea surface actually slopes up towards the ice due to the gravitational pull. And then as that ice melts, then you will get a global average sea level rise, but you'll get a global average sea level rise, but the sea level in the vicinity of the ice sheet that melted will actually fall because that mass is no longer concentrated in this region, and that concentrated gravity anomaly is gone. And so what that means then, the schematic actually notes, is that the shape or the spatial pattern of sea level rise caused by melting of ice will actually vary depending on which ice sheet is melting. So you'd have a very different pattern if you have ice sheet melt in Antarctica versus in Greenland. And this is the, quote, sea level fingerprint for melting of ice in Greenland. And this is calculated using the time variable gravity from GRACE. And this map has been normalized to correspond to 1 millimeter per year of melt from Greenland. That doesn't mean there is 1 millimeter per year of melt from Greenland, but this is normalized in this way so that if there was 1 millimeter per year from Greenland, this is the shape of the sea surface or the shape of the trends. And as we saw in the schematic, you see that the sea level is falling in the vicinity of Greenland and actually rising faster than the melt rate over the far field from the melting source, which covers most of the global ocean. So this is the same fingerprint from Greenland that I just showed you. And again, it's normalized to have 1 millimeter per year global average. what's interesting is if I take my 22 long records that I have and I look at and I sample this map at those 22 locations and take the average, I only get 0.63 millimeters per year. So for any amount of melt from Greenland, these 22 records would underestimate the rate of sea level rise by more than 35%. And then I'm also showing the rate of rise from, or the rate from the fingerprint from the glaciers, also normalized, and then this would underestimate by about 15%. If the melting is occurring in Antarctica, you would overestimate the amount of sea level rise by 15%. So these patterns tell us how much differences, or how much different the trends from one place to another would be due to melting. And these patterns will be different for different sources of melt. The differences would be different for different sources of melt. And then the approach here would be to find combinations of these patterns that are consistent with the differences, the magnitude of the differences between the trends at these tide gauge locations. If you got really lucky, you might be able to constrain the amplitude of these patterns. So we'll at least consider that. And more importantly, what we want to do, however, is get an idea of how much our small set of 20 locations might be under or overestimating the rate of global change. But before we can do that, though, there's another big contribution that we talked about earlier to spatial differences, and that is steric sea level change, or the changes in ocean density. And these differences are primarily due to the phasing of low-frequency climate modes, like the Atlantic multidecadal oscillation or Pacific decadal oscillation. These modes are associated with wind variability, like I talked about earlier, with that force the horizontal and vertical circulation of the ocean, moving heat and salt around and causing density changes. So just for an example here, this is the index of the Atlantic multidecadal oscillation. And just recently there was a paper this summer that associated this index with sea level on the US East Coast, so there is an association there. But you can see is if sea level is indeed correlated with this index, and you calculated the trend over the 20th century, you would likely find a significant trend, despite the fact that this, by definition, has been detrended. So it's just the window that you're looking at, and you can get these, with these multidecadal or decadal oscillations, you can get a trend just from these oscillations within the climate. So then, what does the spatial pattern of steric sea level change look like over the period that we're interested in? Well, we can't know that. We just don't have the observations to do that. But we can use climate models to at least get an estimate of possible patterns. And maybe we can use these patterns in the same way that we might use the fingerprint patterns as well. So I did this by looking at the CMIP-5 ensemble of climate models, where I took 66 historical runs forced by 20th century radiative forcing. I extracted the steric time series from all 22 of those locations nearest to the model. I then subtracted global mean sea level from the steric time series from each model, and then I calculated the trend over that period that we're interested in. And then, since I removed global mean sea level, that means that the mean of the trends of at these 22 locations for any particular model would reflect the degree to which these locations under or overestimate the true global steric trend for that particular model and that particular realization of the decadal variability and multidecadal variability within it. And so then to do this, to get the actual patterns from these trends, I calculated EOFs of the model trends to try and find patterns that are common to each model. As I was just saying, we have all these decadal modes of variability that are internal to the ocean and climate system. But within these various models from model to model, they'll have random phase. And so you get different realizations of how that steric change might look. And I want to point out that you might think it's odd, but I calculated the EOFs at the tide gauge locations themselves instead of the full spatial field. And that was because I really wanted to emphasize the contribution at these locations. And if you do the full spatial field, there's no guarantee that the dominant patterns will be actually useful at those locations. They could get buried in the higher order modes. Okay, so here are the leading trend patterns for these 22 locations from the CMIP, from this ensemble of models. So when I did this EOF analysis, the model itself is the independent variable, right? And so we have trends from each model. The EOF decomposition tells us that this first trend pattern here that has the high amplitude in, or large positive amplitudes in the Atlantic and sort of weak to negative amplitudes everywhere else. This occurs in this set of model runs with this set of amplitudes here represented by this first principal component. And these amplitudes have quite a bit of scatter. This pattern accounts for about 40% of the spatial differences in the trend values at these 22 locations in the models. The patterns can be negative. You see negative values down here. So in some of the models, this pattern looks the opposite of the colors here. So the trends in the Atlantic can be negative relative to the other places. And so that's what I attribute to this random phasing of the decadal to multi-decadal variability within the models. So note then that this pattern does not have a zero mean also. So if this pattern has a positive value, a positive amplitude in a particular model, it will cause a spatial sampling bias by these 22 locations because I've removed global mean sea level. There is no true underlying mean in this for these EOFs. Okay, yeah, so I guess I should mention the second EOF over here as well, and that has a variance of about 28%, or accounts for about 28% of the variance. It has a different spatial structure, but still a good bit of spatial coherence in that pattern. These are probably the only two that are significant based on the eigenvalues, but here are the third and fourth modes as well. These higher order modes account for about 10% of the variance between them. You see that the spatial patterns themselves are quite a bit more noisy spatially from location to location, and the amplitudes are also quite a bit smaller as well. So now what I want to do is try and use these patterns that I have from the models and also the melt fingerprints to say something about global sea level change from those 22 locations. And just to sum up what we know about these amplitudes so far, we know that the pattern associated with these various melt sources. We also have some information about the amplitude of the glacier melt fingerprint. There are some observations there. The IPCC report, based on observations and models, constrains that to somewhere like 0.4 to 0.9 millimeters per year. But we don't have really much information at all about how to scale these Greenland and Antarctic patterns. They're completely unknowns. We know that observations are not sufficient to calculate the pattern of steric change during 1901 to 1990. We just don't have that kind of information. But what I've tried to do from these EOFs of the climate models is get an idea of what the dominant patterns might look like at these locations, get a good idea of the likely amplitudes of those patterns as well. So now what I want to do is try to look for combinations of the melt fingerprints and steric patterns that account for at least some fraction of the spatial differences in the observed trends. And then try to quantify the uncertainty a little better and get a distribution of the sampling biases that might result from these various spatial structures. So the problem is because we only have 22 gauges, or 22 locations, these patterns are highly correlated at those locations. And so we can't just do a least squares fit to them. But instead, we do have the computing power to do a brute force search over all the possible amplitudes of these patterns and all the possible combinations. And so I did this search, and for one iteration, this is what I did. For one iteration, I would choose random amplitudes of the patterns for which we have some information to constrain them. So for the glacial fingerprint, I would choose a random amplitude between 0.3 and 1 millimeter per year. For the first four EOFs that I showed you from the models, for the steric patterns, I would choose an amplitude that was consistent, or within a range that was consistent with sort of the maximum absolute value of the amplitude in the principal components. So the maximum amplitude or absolute value for the first one was about 3, about 2.5, and a little less than 1 for these as well. So then I scaled the patterns by these random amplitudes and subtracted them from the observed trends. Then I fit the amplitudes for which we have no constraints. I don't have any idea of a range to give to these Greenland and Antarctic patterns, so I just fit them after removing that. And that's okay because these two patterns actually are not significantly correlated at those locations, just the two of them. Okay, and then, so I generated about 30 million of those combinations with those random amplitudes. And I applied two further constraints. The first being that when I subtract the scaled melt and steric patterns, I have to reduce the variance in those 22 trends. And that's just akin to the assumption that I'm assuming that at least some fraction of the variability is related to those patterns. So if I subtract that variability, it shouldn't get worse, the scatter. I also imposed that the sum of the total melt fingerprints, the amplitudes of those melt fingerprints, must be between 0 and 2 millimeters per year. So that I'm just assuming that there is some melting going on over the 20th century. I'm not saying where, but there is some melting, and I'm also saying it can't be unrealistically large either. And so when I do that, that leaves just 2.5 million of the 30 million combinations. And now I'll show you some results based on those 2.5 million combinations of patterns. So these top two figures show the probability density functions of the fitted melt rates that I got from the Greenland and Antarctic ice sheets. So these were the ones that were not constrained at all, so I fit them. And I was hoping that maybe I could, there would be enough spatial information here to constrain the amplitudes of those patterns and hence the melt rate from these different locations. Clearly that's not the case though. This distribution of these amplitudes when I try to fit them is quite broad. The distribution of the Antarctic ice sheet is skewed toward the positive, but there's still a 1 in 5 chance based on this PDF that it could be negative, so I'm not even sure I can really say that the Antarctic is positive either. But in contrast to fitting these amplitudes, if I look at the PDF of the total sampling bias, when I look at the spatial patterns or how the locations are sampling these patterns of the melt fingerprint and the steric, the sampling bias actually is fairly well constrained. And the median of this PDF is right about negative 0.1 millimeters per year, where the sign means that these gauges would tend to systematically underestimate the true global trend. This distribution also indicates that there is no combination of the patterns that satisfy my constraints that will lead to these gauges overestimating the global trend, which I think is really interesting and a surprising result. So then we can look also at how the trends at the individual gauges were affected by imposing these spatial patterns on the observations. The gray circles here are the observed tide gauge trends again. The blue circles are the medians after doing the fits. And the vertical lines show the ±1 standard deviation range at each location. And these are important because we can use these as the uncertainty when we calculate and propagate these uncertainties through when we calculate the mean of these trends. And so when we do that, when we propagate these as uncertainties as opposed to doing the standard error, we get an error or an uncertainty in the sample mean that is 50% larger than the standard error calculation I showed you earlier. And if we do a PDF from that, that's what this looks like. So this will be centered on the mean value of the mean of the observed values, which is 1.5 millimeters per year. But then what we want to do is get a PDF of what the mean would be for the true underlying global mean surface, or the global surface that is sampled by these tide gauge locations. Not the sample mean itself, that's what this is, but we want to get the PDF of the true mean of the underlying surface. So that would be the sample mean minus the sampling bias. And so if you want to get the PDF associated with that, you just do the convolution of these two PDFs here, and we get this. So that's the distribution for the true underlying surface based on the locations of these 22 tide gauges, which have a mean of about 1.5 millimeters per year. And so the gray shading in the background here indicates the 95% interval for this distribution. And I'm showing the mean of the observed trends, like I just pointed to here with the black dashed line. And I also put the reconstructed rates as well on here for the Hay, the Church and White, and the Ray and Douglas reconstructions. Where now we can say that the Church and White and the Ray and Douglas reconstructions are not statistically inconsistent, at least, with the long-term trends in these records. But I would say that, at least in terms of these results, that there's very little probability that the 20th century trend from the Hay reconstruction is consistent with the observed trends from the longest and the best records that we have in terms of tide gauges. And so if you want to extrapolate a little bit from these results, you could say that we're on the smaller acceleration track. That's probably pushing the capabilities of this analysis a bit too far, however. Okay, so that's what I have, and I'm just going to sum this up. First of all, prior to the satellite era, estimating global sea level rise is quite difficult due to the constantly evolving tide gauge network and large-scale spatial structures that are in sea level due to steric variability as well as melt fingerprints. There have been a variety of methods that have been developed to combine this tide gauge data, use more of the tide gauge data, including short records, and then combine that with spatial information from altimetry to get better estimates of global sea level change. But part of the 20th century, or the variance in these 20th century rates, is due to the particular subset of gauges that was chosen by each of these reconstructions. And so this may indicate that these methods are not completely able to capture what they're trying to do. And so the sensitivity of the global estimates to that particular set of gauges motivated us to go sort of in the opposite direction. That instead of including more and more data, let's look at the highest quality long records again, like we did before, and find a way to potentially assess these reconstructions based on the long-term trend. Of course, working with this only small handful of gauges is challenging in itself for all the reasons that I just showed, but it is a feature that we think we can reliably capture with this long set. And so it can serve as a way to vet these various reconstructions. And so based on the locations of these long records, as well as the spatial structures that I included here, we find this set of gauges is most likely to underestimate the long-term trend, which in turn suggests that the global reconstructions that are most consistent with the best tide gauge data we have in terms of the long-term trend are the ones that would give a trend during 1991 or 1901 to 1990 that is greater than the mean trend from these 22 records, which is 1.5 millimeters per year. And I'll leave it at that. Thanks.